Hello everyone, this is Group 8 presenting our final project for EEE 304 Digital Electronics Laboratory titled Design and Implementation of an FPGA-based vending machine using Verilog. Here's the roadmap for our presentation. We'll start with an introduction to vending machines and FSM-based design, review related literature and limitations, discuss FSM types, detail our design and testing, and conclude with a demonstration. The primary objective of our project is to develop a user-friendly vending machine system implemented using a finite-state machine, or FSM, on a Field Programmable Gate Array. The machine will be able to mimic all the crucial functions such as accepting coins, dispensing products, and providing a user feedback. While existing studies have explored FSM-based vending machines, limitations remain. For instance, previous designs only accept specific denominations and lack incremental cash addition. Our method is implemented to address these two issues. Now, we are all more or less familiar with what a vending machine is due to its increasing popularity in recent years. It is essentially a self-service machine which operates by inserting coins, selecting a product, and dispensing the product if the inserted amount is sufficient. Additionally, they return change if excess cash is provided during the transaction. Before we dive deep into this presentation, let's clarify some key terms. A finite-state machine is a sequential circuit that uses a fixed or finite number of states. At any given moment, the machine resides in one particular state. Depending on the given input, it jumps from one state to another, a period known as transition, and the total number of states is referred to as the modulus. A state diagram represents this visually as a directed graph consisting of nodes and arrows, where the nodes indicate a specific state and the arrows indicate transition between these states. There are two types of FSM, Moore and Mealy. In a Moore FSM, the output depends solely on the current state, while in a Mealy FSM, it depends on both the current state and the inputs. For our project, we have focused on the Mealy type. This is the synchronous sequential circuit for a Mealy-type FSM. A clock signal is used to control the operation of this sequential circuit, hence the name synchronous. The output is dependent on both the past behavior of the circuit as well as the present behavior of the inputs.
To implement our idea, we had to decide our inputs and outputs. In our code, we declared a clock and reset option as input. Whenever a user puts some coin in the vending machine, he has to press the clock button to make sure the money is received. However, the reset button is kept to indicate the consumer has bought his wanted product and the machine is ready for another consumer to buy another product. Our vending machine contains various types of products. All of them are of 10, 15, 20 or 25 taka. A user has to select which product he wants to buy, then our vending machine can receive 5, 10 or 20 taka notes only. A user can give only any of the three notes according to his product's price. After that, he has to press the clock and observe the change in the LEDs which indicate the present state and next state diversion of the money added. Apparently, it doesn't have a significant value to a user. However, if the product is bought, the rightmost green LED will glow and the leftmost LEDs will show the return money if there is a change. The state diagram is drawn for 10 taka product, which contains two states, 0 taka and 5 taka. As it is of a Mealy-type FSM, the output depends on every input, which is shown here. The state table and state assign table is also shown, which can help us further to implement the sequential circuit in hardware. However, we observed two test cases for 10 taka product. Firstly, we gave 5 taka. The vending machine would not allow to buy the product because of enough amount is not inserted. If we put 5 taka again, now it has complete 10 taka and it is showing the purchase is done with 0 changes. The purchase is done with 0 changes. However, we gave 20 taka to the machine. Now the enough amount is inserted and the cash return is 10 taka and the purchase is done. The state diagram is drawn for 15 taka product, which contains 3 states, 0 taka state, 5 taka state and 10 taka states. The state table and state assign table is also shown. Here we observed one test case where we gave 20 taka note to a 15 taka product. So enough amount is inserted, the product is purchased, and the cash return is 001. That means cash return is 5 taka.
Here I will present the state diagram for our vending machine project specifically tailored for a product priced at 20 taka. This diagram provides a clear visualization of the states and transitions within the machine's operation. We can see the diagram consists of four states represented as S0, S1, S2 and S3. S0 represents the starting state where no money is inserted or the product is purchased. S1, S2 and S3 corresponds to accumulating 5, 10 and 15 taka respectively. The transition between the states are guided by the money input and the machine's response. The notation on the arrow, such as money, purchase, change, indicates the amount inserted, whether the product is dispensed, and any remaining balance returned. For example, moving from S0 to S1 happens when 5 taka is inserted. With no product dispensed yet, once the full amount of 20 taka is accumulated, the machine transitions back to S0, dispensing the product and any change if applicable. We observed one test case for 20 taka product. Firstly, we gave 5 taka. The vending machine would not dispense any product because enough amount of money is not inserted. Then we put 20 taka again. Now it has enough amount of money of total 25 taka to buy a 20 taka product. And now it is showing the purchase is done with a 5 taka cash return. Next, I will present the state diagram for a product at 25 taka. The state diagram consists of 5 states. Here, S0 is the initial state representing no money inserted or a product being purchased. S1, S2, S3 and S4 indicate the progression as the user inserts 5, 10, 15 and 20 taka respectively. The transition between these states are governed by the money input and the machine's response. If we insert enough amount of money, the machine will dispense the product and transitions back to S0, providing any necessary change. Then we have observed a test case for 20 taka product. Firstly, we gave 20 taka. The vending machine would not dispense any product because enough amount is not inserted. Then we put 10 taka again. Now it has enough amount of money of total 30 taka to buy a 25 taka product. And now it is showing the purchase is successful with a 5 taka cash return.
Now we are going to explain the code for the product of 20 taka when 10 taka, 5 taka and 20 taka notes are inserted respectively as cash inputs. This input combination is supposed to purchase the product and return 15 taka. In this case, 0 or 20 taka state is defined as state 0, whereas 5 taka, 10 taka, and 15 taka states are defined as state 1, state 2, and state 3 respectively. Here we can see that when present state is at state 0, inserting 10 taka, which is defined in binary as 2B10, will result in the next state to be state 2. From this state 2, inserting 5 taka which is defined as cash in 2B01, will take the next state to be state 3. Now, the product is not purchased yet, and there is no cash return as sum of total is not equal to or more than 20. Now, from this state 3, inserting cash input 20 taka, which is defined as 2B11, will return the next state back to be state 0, but this time the purchase will be done and the cash return will be 15 taka. And this is the work distribution among our project members. There are some limitations of our project, as pressing the reset button at any point of the procedure will stop it immediately without returning the previously entered money. There are limited currency input as only 5, 10, and 20 taka notes can be used. Also, as outputs are shown in FPGA board in LED instead of a display, system is not user-friendly. And this is the user manual for our FPGA implementation, showcasing directions for the product selection, cache input, cache return, and output. And here are our group members. Thank you.
আচ্ছা, আমার ভেন্ডিং মেশিনে আমি 25 টাকার একটা চকলেট কিনতে যাইতেছি। তো আমার কাছে 5 টাকা ছাড়া আর কোনো নোট নাই এখন। তো 25 টাকার প্রোডাক্ট কিনতে গেলে আমার 5 টাকা নোট লাগবে হচ্ছে 5টা। তো আমি 5টা নোট দিব। নোটটা দিয়ে আমি আসলে দেখবো যে আমার ভেন্ডিং মেশিনে প্রোডাক্ট কেনা যায় কিনা। তো আমার ভেন্ডিং মেশিনে আসলে অনেকগুলো প্রোডাক্ট আছে, অনেক ধরনের প্রোডাক্ট কেনা যায়। 10 টাকা, 15 টাকা, 20 টাকা, 25 টাকা প্রোডাক্ট কেনা যায়। তো আমার ইউজার ম্যানুয়াল আছে, ওটা দেখে আসলে আমি বুঝছি যে 25 টাকা প্রোডাক্ট কিনতে গেলে আমার এইটা আর এটা জ্বলে থাকবে। আর শুধু এইটা অন রাখা মানে হচ্ছে আমার 01, মানে 5 টাকা আমি ক্যাশ ইন করতেছি। তো 5 টাকা যদি আমি 5 বার ক্যাশ ইন করি তাহলে আমার 25 টাকা প্রোডাক্ট ঠিকবে। তো আমি 25 টাকার প্রোডাক্ট সিলেক্ট করে দিছি। এখন আমাকে 25 টাকার প্রোডাক্টের জন্য সে কাজ করবে। তো আমি 5 টাকা দিলাম, আমার প্রোডাক্ট কিনা হয়নি। প্রোডাক্ট কিনা হলে আমার এই বাতিটা জ্বলার কথা। আচ্ছা, আমি এখন আবার 5 টাকা দিলাম, আমার প্রোডাক্ট কিনা হয়নি, কিন্তু আমাকে সে দেখাইতেছে যে সে 10 টাকা পাইছে, তার কত টাকা বাকি আছে। আচ্ছা, এখন আমি আবার 5 টাকা দিলাম। আচ্ছা, এখন সে দেখাইতেছে যে সে আসলে 15 টাকা পাইছে এবং তার যতটুকু বাকি আছে সেটাও দেখাইতেছে। এবং এখনো যেহেতু 25 টাকার মধ্যে মাত্র 15 টাকা আমি দিচ্ছি, আমাকে কোনো প্রোডাক্ট পারচেস করতে দেয়নি। আচ্ছা, এখন আমি আবার 5 টাকা দিলাম। আচ্ছা, এখন হচ্ছে সে কত টাকা পাইছে, 20 টাকা, কারণ আমি 4 বার দিছি এবং সে তার কত টাকা বাকি আছে সেটাও দেখাইতেছে এবং এখানে পারচেস হয় নাই সেটাও দেখাইতেছে। সো এটা আমার লাস্ট আমার কাছে এইটাই লাস্ট নোট ছিল। আমি এখন আবার 5 টাকা ক্যাশ ইন করবো। এখন আমার প্রোডাক্টটা পারচেস হয়েছে এবং আমার কোনো টাকা রিটার্নও করেনি, যেহেতু আমি এক্সট্রা তাকে কোনো টাকা দিইনি। এই ছিল আমার 25 টাকার প্রোডাক্টের জন্য ভেন্ডিং মেশিনের কাজ করে।